Welcome to the demo for 9.1, Hypothesis Testing for One Mean. We're going to use the sample data from before with the M&M weights. We're going to use that sample to test the company's claim that the average weight of a fun-size bag of M&Ms is 13.5 grams. We're going to test this claim at the 5% level of significance. Before we can run a hypothesis test, we need to be sure we have a normal sampling distribution. This can happen if the population is normally distributed. We do not know for sure that the population weights of fun-size packs is normally distributed. Or if we don't know the population is normal, we have a large enough sample size. So I've taken our sample data and created a histogram. This histogram looks approximately symmetric, certainly not perfectly, but approximately. We know if we have an approximately symmetric distribution, we only need about 15 data points for that sampling distribution to be approximately normal. Since we have 33 data points, we can assume our sample means are approximately normally distributed. So we're going to use the sample data from our M&M's weight file to test this claim. What are the null and alternative hypotheses? So the company claims that the average fill is, remember in math, is means equals, is 13.5 grams. Let's say that we want to test to see if they're actually filling the bags properly. Our null hypothesis would be equal to 13.5 grams. Remember, the equal to sign always goes on the null. It doesn't matter if it's greater than or equal to, less than or equal to, or just plain old equal. That always goes in the null hypothesis. The null hypothesis is the thing we're going to assume true until we collect enough evidence to prove it wrong. In this case, we want to start by assuming that the company is filling the packages correctly, until we collect enough evidence to say the company is overfilling or underfilling the packages. Underfilling is a problem because then the customer is not getting what they want, and we might get in trouble with the departments of weights and measures. Overfilling is also a problem. If we're overfilling, we're giving away our profit. So how would we draw a picture for this particular hypothesis test? We always start by assuming the null is true. Assuming the null is true means assuming that the center of the distribution is at 13.5 grams. What we're trying to do is see, is our sample value way below 13.5 or way above 13.5? So far away that 13.5 does not seem to be the true mean. We're going to use a sample mean to do this. So we're looking at the sampling distribution here. We're going to find a sample value, a sample mean, and see if that sample mean is way far away or unlikely to happen if 13.5 is actually the mean. If we are able to reject the null, in other words, we get a value for our sample mean that's way far away from 13.5, we are then able to accept the alternative. So here is our sample data from the M&M's weighing that was done before. I've run descriptive statistics on this information. From this, we can capture our mean and our sample standard deviation. For what we're doing right now, that's all the information we need. We're going to start by using the critical value approach to hypothesis testing. I'm going to show you several approaches. Each of those 4 approaches are mathematically equivalent. So I'm going to start with the critical value approach because I believe it's the one that makes the most intuitive sense. For this problem, we have to use the t distribution. We do not get to use the z distribution. We have to use the t because we've got a sample standard deviation. We're going to compare a t-score to a t-critical value. The t-critical determines the rejection region. We calculate the t-critical by using t.inv. Since we're trying to test with a level of significance of 5%, alpha is 5%, and we have a two-tailed test, we divide alpha by 2, and we use 2.5% in our t.inv. Our degrees of freedom here is 23 minus 1. Degrees of freedom for now is always n minus 1. You could also use t.inv.2t and leave alpha whole there. Either way, we get a t-critical value of 2.0739. This actually tells us that our sample statistic needs to be more than 2.0739 standard deviations away from 13.5 to be considered far away. In other words, to be able to reject the null hypothesis. Our t-score comes from the sample data. So you calculate the t-score just as we've done before. X bar minus mu. In this case, mu is going to be the mu from the null hypothesis. So I put mu sub h to remind myself that this is a hypothesized mean. Divide by the standard error, s over the square root of n. From descriptive statistics, we calculated the sample mean to be 13.1003. Our hypothesized mean is 13.5 because the company claims that on average, those bags are filled to 13.5. If you just look at those two numbers, it might look like consumers are actually getting cheated on product. But let's see if 13.1 is way far away from 13.5. So divide by the standard deviation over the square root of n. When we do this calculation, we get a t-score of minus 1.82. In other words, our sample value, x bar, is only 1.82 standard deviations below the hypothesized mean. We should always put this on the picture because it's just easier to see. Our 13.5 was our hypothesized mean. We've got 2.5% in each tail. The t-critical value demarcates these rejection regions. So we need to be at least 2.0739 standard deviations above the mean or minus 2.0739 standard deviations below the mean to be able to say that our sample value is way far away from the mean. Our sample value happens to be right here. It's only minus 1.82 standard deviations below the mean. So our sample value is not far enough away to say that we can reject the null. Since the t-score is not in the rejection region, in other words, it's not in the tail beyond the critical value, we cannot reject the null hypothesis. There is not enough evidence to say that the fun-sized bags of M&Ms are being filled differently than 13.5 grams. In other words, we cannot say that they are underfilling the bags of M&Ms. Another way to calculate this and to do the comparison is to do the critical value approach, but in the original units. So instead of calculating in standard deviation terms, we're going to calculate this in grams. That's actually more useful to some tech who may not know statistics very well. To do this is actually quite easy. We're going to take the hypothesized mean, that 13.5, and go up and down from that, basically what's equivalent to the margin of error. Do not call this a confidence interval. This is not a confidence interval. But I'm going to calculate a range of values inside which our sample value should be if our machine is operating properly. If the sample weight is outside of this range, we would say the machine needs adjusted. So for this case, our hypothesized mean is 13.5 plus or minus this critical value of 2.0739 times the standard deviation of that sample, 1.0525, divided by the square root of 23, which was our sample size. If we simplify this, we get an x bar low of 13.04 grams and an x bar high of 13.96 grams. In other words, if our sample value is inside those two boundaries, then we would say our machine is operating properly. If our sample value is outside those two boundaries, we would reject the null and accept the alternative. We would know we need to adjust the machine. So what we've done is find out in gram terms where these cutoffs happen to be. So this cutoff is 13.04. This cutoff is 13.96. This should actually feel much like the French fry problem we worked on about Simplot Foods and the 6-inch long French fries. So we've got this lower boundary, 13.04, this upper boundary, 13.96. If we're inside this range, we would not reject the null hypothesis. If we're outside that range, we would say we need to adjust the machines. We're going to reject the null hypothesis. For our example, we're at 13.1003. We are inside that range. We cannot reject the null hypothesis. Since the sample mean of 13.1003 is in between these two numbers, we cannot reject the null hypothesis. We do not have sufficient evidence to conclude that the fun-sized bags of M&Ms are being filled to something other than 13.5 grams. We're now heading on to the third approach. It's the p-value approach. The p-value is the probability of getting a sample mean as far or farther away from 13.5 as we happen to get, assuming that 13.5 is the true mean. So we're going to pretend 13.5 is at the center of our distribution, and we're going to find the probability. Because this is a t-dist problem, we have to use this function called t.dist. We haven't used this before. If you need to use t.dist, you're going to plug in here the t-score. Now, I'm going to show you how to do this in Minitab, so you won't actually have to follow this process if you don't want to. We're going to find the probability that a sample mean could be less than or equal to 13.1003, assuming 13.5 is the true mean. Remember that t-score was negative 1.82, and we had 22 degrees of freedom. The reason that we multiply by 2 is because we have an equal to or not equal to scenario. When you have cases of strictly greater than or strictly less than, you need not multiply by 2. This is going to calculate the probability to the left of negative 1.82, and then we want to multiply it by 2, because it's possible, when we're doing a two-tailed test, that our sample mean could be way, way below or way, way above. So we want to calculate the probability of being that far or farther away from the mean in either direction. That is only necessary when you have a not equal to. Now, Minitab will automatically do the 2 times for you, so you don't need to do any of this if you choose to use Minitab. The p-value here tells us there's an 8.2% chance that we could get this sample mean or something even further away in either the lower direction or the upper direction if 13.5 is the true mean. This actually means for us that our 13.1 had a 4.1% probability of being less than or equal to that. We multiplied that by 2 and we got 8.2%. Since the p-value is greater than alpha, we cannot reject the null hypothesis. We do not have sufficient evidence to say that the company is filling the packages to an average that's different from 13.5 grams. You may already be noticing we're making the same conclusion with each of the methods we're using. All 4 approaches are mathematically equivalent. Now, I want to show you how to do this in Minitab, and while I'm doing that, I'll show you the 4th method. So in Minitab, to perform this hypothesis test, we're going to go to a tool we already know. Stat, Basic Statistics, 1 sample t. Since we have a column of data, we're going to leave the drop-down box in the column mode, and click into this box and double-click your variable into that box. Something new, though. We will now check the box next to Perform Hypothesis Test. And in here, we will enter the value that we've put in our hypothesized mean. So we've assumed that they're meeting their goal of 13.5. That's our hypothesized mean. We also need to go into the options box, which is what you see on the right. We're going to double check that our confidence level is correct. In this case, we're using a 5% level of significance, so that's a 95% confidence level. We also now may need to change the alternative hypothesis. For this case, we are using the not equal to in our alternative hypothesis, so we're going to leave that. If our alternative hypothesis had a greater than, we would change the drop-down to greater than. If it had a less than, we would change the drop-down to a less than. Make sure to match those up. Hit OK again, and here is our output. The 4th way that you can actually test a hypothesis is using the confidence interval. Remember, this confidence interval was generated using x bar in the center of it and calculating these 2 boundaries. So we can look to see, is mu, that hypothesized mean, inside the interval? If mu is inside the interval, it is possibly the mean. So we cannot reject the null, because remember, we're 95% sure that the true mean is inside this interval. If mu is not inside this interval, we're pretty sure then that mu is not the mean. Remember, we're pretty darn sure that the true mean would be inside this interval. Since the hypothesized value of 13.5 grams is inside the confidence interval, we cannot reject the null hypothesis, because the true mean is likely inside the interval. There is not sufficient evidence to conclude that the fun-size bags are being filled to an average that's different from 13.5 grams. Now, before we go off of this output, I want to show you that the t-score and the p-value are generated right here in Minitab. When I'm performing hypothesis tests, I typically just use the p-value approach. The p-value is quite quick and easy to generate using a program like Minitab, and then I need only compare to alpha. Since alpha is given or assumed, I can quickly determine this value is greater than 5%, and since this value is greater than 5%, I cannot reject the null. So I strongly encourage you to get into Minitab and try it, and use the p-value approach. Thank you for watching. I'll see you again soon.